Thanks very much. I'd like to thank the organizers of this conference, which has been really great, and also the scientific committee for all the work that they did. So you can see my title by V-graded categories and V-W-bigraded categories. And we'll use these concepts to provide a way of treating functor categories and bifunctors over non-symmetric bases. And this is a bit analogous to the question of functor categories in enriched category theory, for which, the familiar case is where V is symmetric, and then we can, with some limits, we can form enriched functor categories. But here we'll do something different that will allow us to form functor categories over non-symmetric bases. So to start off with, we'll look at this concept of a V-graded category. Let V be a monoidal category. And we'll assume that V is set small for some category of large sets, capital letter set. So this doesn't mean that V is small, but just that it's internal to this category of large sets. And then we'll form the presheaf category, the functor category from V off to set, and equip it with the deconvolution monoidal structure. And then we can consider the following definition. A left V-graded category, or simply a V-graded category, is by definition a V-hat category. So V-hat is our notation for this, for the presheaf category with deconvolution. We look at categories enriched in that, V-hat categories, and we're simply calling those V-graded categories. And I'm introducing this prefix left here because later we'll also look at right V-graded categories and also bi-graded categories. This concept of V-graded category was introduced by Richard Wood under the name large V categories. And it was also studied in a more general bicategorical setting by Kelly, Labella, Schmidt, and Street, who called these pro-categories. And the V-graded categories were also used by Garner in working in proving an embedding theorem for tangent categories. And as part of that, Garner described tangent categories as certain actagories and therefore as certain V-graded categories. And Levy has called these V-graded categories locally V-graded categories. So in terms of the terminology, I've just chopped off the word locally and arrived at the term V-graded categories. And V-graded categories have been employed very recently by McDermott and Ustalu in computer science. All right. So first of all, to make a few remarks about what we'll do in this talk, I wanted to first mention some of the advantages of V-graded categories. Well, first of all, V-graded categories are certain enriched categories. But on the other hand, V-graded categories can also be regarded as more general than enriched categories, because V-graded categories generalize both V-enriched categories and also V-actagories, as we'll see in a moment. V-actagories play an important role in computer science, particularly in view of the role of strong functors in computer science, because these strong functors are lax morphisms of actagories. And so this point of view becomes especially natural when we begin to regard V-graded categories as an elementary concept in their own right, which admits an elementary element-wise definition that's quite easy to work with, even for beginning students. And then a further advantage of V-graded categories is that we don't need to assume anything about the base V, the monoidal category V, because the base of enrichment that we're employing here, V hat, is always biclosed, complete, and co-complete. So we can apply the methods of category theory enriched in a biclosed, complete, and co-complete category. And in particular, we can employ work on categories enriched in locally co-complete bicategories. And so we get a rich calculus of modules, and, for example, weighted colimits. And also we can even form V-hat enriched presheaf categories valued in V-hat using a construction of street. And when V is symmetric, then V-hat is also symmetric, and we can employ the full-blown methods of category theory enriched in a symmetric monoidal closed base. But similar remarks apply also when V is braided, or even more generally, when V is normal duoidal, because in that case, we can employ the work of Lopez, Franco, and Garner to form V-graded functor categories and employ V-graded bifunctors. But in this talk, what I'll do is introduce a theory of V-graded functor categories and bifunctors that applies when we don't assume anything about V at all, just a monoidal category V. So we don't even equip V with any further structure. And the resulting formalism differs in some notable ways from the usual approach that's available in the symmetric setting. And the approach that we'll see seems to employ some features special to V-graded categories. And so I think that this illustrates the idea that in addition to generalizing both V-enriched categories and V-categories, V-graded categories open up some new possibilities that one would have never considered in the enriched setting. And we'll see how different the approach is in a moment. Okay. So, what we'll do now is suppose that V is strict monoidal. So when V is strict monoidal, we get a particularly simple element-wise definition of V-graded categories. And in fact, there is, of course, a reason why we can, without loss of generality, in a certain sense, assume that V is strict monoidal. We can even employ the strictification of an arbitrary monoidal category V, in which the objects are lists of objects of V, and of course these are regarded as representing a tensor product of the given object. So in fact, of course, certainly it's not much of a restriction to suppose V is strict monoidal. And then, a V-graded category, C, consists of the following data. A set, obc, of objects, so like an ordinary category, these V-graded categories have objects. But then, instead of having Hom sets, a V-graded category has presheaves like this, from an object A to an object B. And we're introducing this new notation for these presheaves. I'll write them as script C blank, and then this comma-like symbol, A semicolon B. The comma-like symbol is not actually a comma, but for most purposes you can write it as certainly as a comma, and it will make no difference. But here I use a different symbol, which I call a tick, and I'll read it as tick, just because we'll see it's at times useful to distinguish it from a comma. So we can read this as script C blank tick A semicolon B, or just script C blank A B, and that's a presheaf on V valued in set. And we know what the data for that consist of in more detail. And we have also composition. Composition is provided by a family of maps of this form. You can take a moment to look at what they do. And these are required to be natural in Y and X in V. So we'll think about what these do a bit more in a moment when we unpack this even further. We also want identities, which are elements of this form in these sets, where we take the object, the first object here, I, that's the unit object of V. And then we impose some axioms. We require that the composition be associative, strictly associative, and that 1 sub A serve as an identity for composition, a strict identity. So we can also do this, of course, when V is not assumed strict monoidal, but just an arbitrary monoidal category. And then what changes, all we have to change is just that the associativity becomes non-strict, and the statement that one sub A is an identity also becomes non-strict. Okay, so with those modifications we can describe V-graded categories in this form also for arbitrary V. But it's super convenient at times to work with strict monoidal categories. Okay, so let's unpack this a bit more. I won't cover this fully, the fully element-wise unpacked definition, but what we'll do is instead introduce some notation that we'll work with throughout the talk, and it'll become quite evident what the unpacked formulation of V-graded categories is. So let's see a V-graded category, and then we'll use the following notation. We write this expression, F colon X tick A arrow B, to mean that F is an element of the set on the right there. And we introduce a name for these elements. We call F a graded morphism with grade X. And so a V-graded category has what we call graded morphisms, and the grade of such a graded morphism is an object of V. So for example, every pair of graded morphisms of the given forms, composable graded morphisms then, each such pair has a composite, G of F, whose grade is the monoidal product, Y tensor X. And also, if we're given a graded morphism, written in this way, in C, and also a morphism alpha from Y into X in V, then we can sort of pull back this graded morphism along alpha, and we obtain a graded morphism alpha upper star of F with grade Y now, that we call the reindexing of F along alpha. And we can, of course, form the two category of V-graded categories. Since they are V-hat enriched categories, we can form the two category of V-hat enriched categories. We call this the two category of V-graded categories, left V-graded categories. We'll see right V-graded categories soon. And we use this notation where we put the V in a subscript on the left. And the one cells here are what I call V-graded functors, or left V-graded functors. And a left V-graded functor assigns to each graded morphism, F, a graded morphism of the given form. Of course, it has also an assignment on objects. And a V-graded functor preserves composition, identities, and reindexing. The two cells here I call V-graded natural transformations. And writing them in the standard way, such a thing consists of a family of graded morphisms, but here where the grade is I, so these are actually morphisms in the underlying ordinary category of D. And we have a family of morphisms of this form, such that for every graded morphism F of the given form in C, the domain, this equation holds. And it's about the simplest naturality equation we can imagine. This is again for strict monoidal V. So for example, we have the following extremely important two classes of examples. Every V category, V-enriched category, may be regarded as a V-graded category. And how do we do that? So it's a V-graded category in which a graded morphism of the given form is defined to be a morphism F from the grade X into the Hom set, the Hom object rather, Hom object script CAB in V. So this is a morphism in V. But then, oh yes, and this gives us actually a fully faithful two-functor from the two category of V categories into the two category of V-graded categories. But then also, we have the following example. Every left V actagory, C, a category with an action of V, may be regarded as a V-graded category as well. And how do we do this? This is even simpler in a sense. In the resulting V-graded category of a graded morphism F of the given form is simply a morphism of this form in C where X dot A, where dot is the action carried by this actagory C. And so, in fact, the notation that I'm employing mirrors the actagory's case. And we'll see this ends up being quite convenient. So the two category of V actagories with lax morphisms of V actagories, or strong functors, embeds as a full sub-2 category of V-graded categories. We have a fully faithful 2-functor. All right. And a further result that we'll make use of is that every V-graded category embeds into a strict V category that we write in this way as V-tic-C by way of a fully faithful V-graded functor from C into V-tic-C. And there's actually a really simple construction of this category. It has objects given by pairs, x comma a, with the first object, x being an object of V, and a being an object of C. And the Hom sets in V-tic-C can be formed using this interesting coend. And I'll use a name for this, the enveloping category or categorial envelope of C. And this ends up being quite convenient. Notation-wise, we'll identify C with a full V-graded subcategory of this category, V-tic-C, via the embedding. And we'll write the action on V-tic-C as tic, and you'll see that this works out very conveniently, because we have examples like the following. Given two composable V-graded morphisms in a V-graded category C, we can take their composite, G of F, which we know the form that takes, but it's equally the following composite in the enveloping category. So this diagram here makes sense in the larger category into which C embeds. Tic here is the action carried by that category. And this actually is the composite, G of F. Okay, so this is the composite. This diagram here denotes a morphism in the V category, V-tic-C, but you can see it actually lies in the subcategory script C, and it is G of F. And so this diagram gives us an expression for G of F in this way, where the dot is the ordinary categorical composition, the usual composition on the ordinary category C. Okay. And this allows us to use diagrams in working with V-graded categories. I call these envelope diagrams. So here's an example, just taking that very same composite, we find that this diagram commutes in the enveloping category. But of course, both composites denote a graded morphism in C. Here's another example of an envelope diagram. If we have a morphism in V from x prime into x, we can consider the reindexing of F along alpha, and this diagram commutes in the enveloping category. Okay, so this diagrammatic language is quite convenient. Now, a right V-graded category is, by definition, a left V-rev graded category, where V-rev is the reverse of V obtained by swapping the monoidal product. And we have a notation for working in right V-graded categories as well. I write the grade on the right instead of on the left. So we write F A tic X to B. And given another such graded morphism, the composite takes the following form. The two category of right V-graded categories can be defined as the two category of left V-rev graded categories. And here we call the one cells right V-graded functors. Okay, now we'll look at a two-sided version of this. Let V and W be strict monoidal categories, and we'll assume this through the remainder of the talk. A V-W-bigraded category I define to be a left V times W rev graded category. And with this definition, we employ also the following notation. The grade of a graded morphism here is a pair consisting of an object x of V and an object x prime of W, but we write this in the following way with x on the left and x prime on the right. And you'll see this is very convenient. I'll use the following notation for the two category of V-W bigraded categories. And then every V-W bigraded category has an underlying left V-graded category and also an underlying right W-graded category. Alright, so some examples of bigraded categories. So this is an important point. V is always V-W-bigraded, and also same for V hat. They're always V-W-bigraded. And then also functor categories valued in V, ordinary categories of ordinary functors valued in V are always V-W-bigraded. And in particular the category, and we can also pass to subcategories, full subcategories of functor categories valued in V as well. So consequently the category of algebras in V of the Levier theory T is always V-W-bigraded.
Sorry, can I ask a question?
Yeah.
Are you assuming here V to be symmetric or no?
No, just an arbitrary strict monoidal category. Yeah, thanks. If in the special case where V is a braided monoidal category, every V-graded category underlies a V-W-bigraded category. Every V-graded category is canonically V-W-bigraded. And then in the more general case where V is normal duoidal, in the sense of Lopez, Franco, and Garner, of course the notion of duoidal category going back further to a number of authors, including Aguirre, in this case, every left V-graded category is, interestingly, V-rev bigraded, but that concept simplifies to simply V times V-graded. Okay. And a further source of examples that generalizes some of the above is the notion of V-W biactagory, which we can define as a left V times W rev actagory C. And we then write the action as a two-sided action with the following notation. And then C is an example of a V-W bigraded category. We can take the enveloping actagory of a V-W bigraded category, and it is also an example of a V-W biactagory. And we denote it with this notation, V tick C tick W, the enveloping actagory of a V-W bigraded category. And in there, we can use the following notation for the action, unsurprisingly. All right, so a first theorem. So we're going to fix a V-W bigraded category C. And then, if A is a left V-graded category, then we can look at V-graded functors from A to C, because C has an underlying left V-graded category, so we can view it as such, view C as a left V-graded category as well. Then left V-graded functors from A to C are the objects of a right W-graded category, which we'll denote in this way. So, usual functor category notation, but I have this superscript and subscript, V and W, indicating that in some sense, this eats the left V grading and exposes right W grading. And similarly, if B is a right W graded category, then right W graded functors from B into C are the objects of a left V-graded category, for which we use this notation. Okay. And so we can look at this in more detail, and a graded morphism in there is a family of graded morphisms in C that satisfy a certain naturality condition, such that for every graded morphism F of this form, this envelope diagram commutes. Okay, I'd like to spend more time on it, but in the interest of time, I'll flip forward. So, we can also perform the following construction to give us a notion of bifunctors. So if we have a left V-graded category and a right W-graded category, then we can construct the following V-W-bigraded category, A box times B. This has objects, pairs, an object of A and an object of B. And the graded morphisms can be written in this form, and they are by definition pairs consisting of a graded morphism in A and a graded morphism in B of this form. So just about the most straightforward product you can imagine, but it's a VW bigraded category. And it is two-functorial in both variables. And then we can look at VW bigraded categories out of this A box times B, and this gives us a notion of bifunctor. And we have a characterization of bifunctors along the usual lines. Such a bifunctor is equivalently given by families of V-graded functors on the one hand of this form, and right W-graded functors of this form that agree on objects, so analogous to the usual characterization of bifunctors, and that must satisfy the following axiom, that for all graded morphisms, F in A and G in B, the following envelope diagram commutes. And then, just to move to the final theorem of the talk, we can ask how this product and this notion of bifunctor interacts with the functor categories that we defined just before. And we get just about as nice of an outcome as we can hope for. There are isomorphisms of the following forms that are two natural in A in left V-graded categories, B in right W-graded categories, and C in V-W-bigraded categories. And that brings us to the end of the talk. Here are some references to works that I've mentioned, essentially in the order in which they're encountered in the slides. Thank you very much.
Thank you, Rory. There are questions or comments? Yes?
I would like to ask you, this enveloping, sorry, envelope cast category, right? The envelope category is like a, can you understand like a completion in some sense?
Yes, yeah. So that's a nice question. So the enveloping category, which we wrote as V tick C, so we're taking a V-graded category C and obtaining a strict category V tick C. That category itself, of course, can be viewed as a V-graded category. And as such, it is the co-completion of C under tensors by objects of V or tensors by representables. And so, yeah, so this is one thing that I meant to mention in the talk, that the enveloping category V tick C has both a strict universal property as a strict category, but also a bicategorical universal property as an category. And so this does also translate in terms to a description of it as a free co-completion of C under certain tensors. Yeah, thanks for the question.
Other questions, comments? Please.
How do your biograded categories compare to the categories enriched on two sides?
Yeah, excellent question. So I mentioned a reference to that paper, right? The Kelly, Labella, Schmidt, and Street paper, categories enriched on two sides. And in there, first of all, they study what they call pro-categories enriched on two sides. Pro-categories is their term for V-graded categories, but in fact they look at pro-categories enriched on two sides. But they have a theorem that allows that two-sided aspect for pro-categories to be reduced to a one-sided description, because you can kind of move one category over. But now, in that paper, they also introduced the concept of category enriched on two sides, of course, and your question pertains to that, and what the relationship might be to these V-W-bigraded categories. And regarding that, I don't know the answer to that question, but certainly this seems like an interesting line of investigation to potentially form connections between these and even categories enriched on two sides. Thanks.
Okay, so if you have a question, I postpone them because it's the last day and maybe someone has the plane or something, so I want to be very strict on the time, and I really thank the speaker again.